redistribution. Redistribution is the process of taking routes from one source and injecting them into another source. So routes from one source are injected into another, well, I should say protocol. And I know that you guys are preparing for your CCIEs and you should know this, but I'm going to explicitly write it anyways. The routes are pulled from the routing table. Now, what I mean by this is that I have seen students sometimes get a little confused. Are the routes pushed out from one protocol into another, or are they pulled in from another protocol into another protocol? So here with this statement, what I'm saying is the routes are pulled in. So when you have source and destination routing protocol, and that's what you always have when you're redistributing, you always have the source of the route and you have the destination. You always pull the route. So you pull the routes from the destination, into the destination from the source. This is not entirely correct, because the way it actually works is that routes from the source are actually inserted into the routing table with the reference what the source was, and then from the routing table they are actually pulled into the destination protocol. So the routes are actually injected into the destination routing protocol from the routing table and not from the protocol. The reason why I'm saying this is that this protocol here has some protocol related database. It doesn't matter what is in this database. The only thing that matters is what is in this routing table injected by this source. So only those routes will be actually pulled in. So this is the protocol that we are configuring to pull the routes in from another source. As I said, this is a very, very basic information, but it is a matter of stumbling point for some people that this intermediary step with the routing table is sometimes forgotten. So I had students who would look into, let's say, redistribution from EIGRP to OSPF, and they would say, but there is the route. I see it in my EIGRP table. Why is it not being inserted into OSPF? Because it doesn't matter that it's in EIGRP table. What it matters is, was it installed in the routing table by EIGRP? If it wasn't installed by EIGRP into the routing table, it will not be redistributed into OSPF, because what is in the routing table may be coming from some other source. So that's number one thing to remember. Another one is a very interesting case, and for this I'm going to use the by now very familiar network of only 3 routers. So I'm going to have R2 connected to R5 connected to R4. So this is serial 000, this is serial 010, and the network here is 192.168.45.0/24, and here I will be using 192.168.25.0/24. Now, what I want to do is I want to have a loopback on R2. Let's say it's 2222/32, and I want to run 2 routing protocols in my network. So it doesn't matter which 2 I'm running. So for this scenario, I'm going to use OSPF on this side, and I'm going to use EIGRP on this side. But it can be any combination of the routing protocols. It could be OSPF and RIP, or RIP or EIGRP. Any 2 protocols, the behavior that I'm about to show you is exactly the same. So I want to have an OSPF adjacency running here, and I want to have EIGRP adjacency running here. So this is what I'm going to set up very, very quickly, not a complicated configuration at all. So on R2, I'm going to say interface loopback 0, IP address. On R5, I already have serial interfaces, but I already had the loopback configured, which I don't care about right now. So I see that I have 2 connected routes. One is connected to a R2, the other one is connected to R4, and on R4, I'm just going to remove the loopback interface that is there. So from R5, I should be able to ping 192.168.25.2, should be able to ping 2, and I should be able to ping R4. So this is the basic connectivity. Let me bring in my notepad. So what I want to do now is I want to configure OSPF between R2 and R4. Oops, sorry about that. So I'm going to say router OSPF1, I'm going to say network 192.168.25.0.255, area 0, and let's advertise the loopback as well into there. So this goes to R2. On R5, I want just this configuration so that I just have the OSPF neighbor between R2 and R5. And then I'm going to configure EIGRP. This is going to be EIGRP 45, no auto summary, and this is 45 here. I don't care about the loopbacks or anything of the sort, so this goes here and this goes on R4. So my EIGRP should come up, and on R5 I should have the neighbor with my R2, and I should have show IP EIGRP interfaces. I can see that I have the neighbor, and this is where I saw the neighbor for OSPF. This is where I'm looking for the neighbor with EIGRP. So now if I do show IP route OSPF on R5, I'm seeing one OSPF route. So what I'm going to configure next is I want to redistribute from OSPF into EIGRP. So a very simple redistribution from OSPF into EIGRP. So I'm going to go to R5, router OSPF1, and I'm going to say redistribute EIGRP. Sorry, redistribute, it's the other way around. So router EIGRP 45, redistribute OSPF1. Now, EIGRP requires me to actually specify the metric in this place, and I can specify anything that I like, and it's simplest to just type all once. So now if I go to R4, if I do show IP route EIGRP, how many routes do you think I'm going to see in the routing table? Well, let's take a look. Let's take a look at it logically. So I'm here now on R5. If I do show IP route, what I'm seeing in my routing table on R5, on a redistributing router, are 3 routes. I'm seeing one OSPF route learned from R2, and I'm seeing 2 connected routes. Now, on R5, I have configured my OSPF to actually inject the route. So I have configured, I apologize, I have configured my EIGRP to inject the routes that have been installed in the routing table by OSPF. So there is one route that matches this description. So the logic would tell me that on R4, I should actually have a single EIGRP route in my routing table. But in fact, I will have 2 routes in my routing table. I will have 2.2.2.2, which is the route that I expected to see, but I'm also going to get this route. So this route as well got installed and redistributed into EIGRP. Now, why did this route get redistributed? And as I said, it doesn't matter which protocols I'm using on these 2 sides, the behavior is always going to be the same. This is the default behavior in iOS. This interface here, serial 020, and it's also serial 020 on this side, is enabled for OSPF. So OSPF actually installs information about this interface in its protocol-related database. iOS also knows that this interface is actually enabled for OSPF on this router R5. So when I say redistribute OSPF routes into EIGRP, what is going to happen by default is that learned routes, learned OSPF routes, are going to be redistributed, but also connected interfaces or connected routes of interfaces enabled for OSPF. So even though this was a connected route, it will actually end up being redistributed because of this implicit redistribution. So that's the reason why in my routing table I get two routes, one that I expected and one that I might not have expected. But this is not where the story ends. Let's expand our example just a little bit. So we are still dealing with the same network. So here we have R2, R5, and R4. Now I want to add two loopbacks on R5. So let's say that I have loopback 0, which is going to be 5.5.5.5/32, and let's say that I have loopback 5, which is going to be 55, 55, 55, 55/32. And the task here says very simple instruction. So on this side I'm running OSPF. On this side I'm running EIGRP. The task says a very simple thing. Redistribute loopback 0 into EIGRP, but do not redistribute loopback 5. Okay, this should be a relatively simple thing to do. So let me go to my terminal. So what I'm going to do first, I'm going to create my two interfaces. So I'm going to go to R5. So I have created my two interfaces, and then what I need to do is I'm going to create some sort of filters. Now there are multiple ways I can do this. I can use route map with access list. I can use route map with prefix list. I can use route map with match interface. Any method I use, it doesn't matter, the behavior will always be the same. So I'm just going to use the simplest one. Let's say I want to say route map connected to EIGRP, permit 10, and I'm going to say match interface loopback 0, because this is the only one that I actually want to redistribute in there. So I don't want loopback 5 to be redistributed. And then I'm going to say router EIGRP 45. I'm going to say redistribute connected route map connected to EIGRP metric. Again, I have to specify the metric. So this is the configuration that I'm going to paste in to my R5 now. So at this moment, I'm redistributing loopback 0 into my EIGRP. Let's see what is the situation now on R4. If I do show IP route EIGRP, take a look at the two routes that I now have in my routing table. I have loopback of R2, the one that I had before, and I have loopback 0 of R5, the one that I just redistributed. But this route has now disappeared from the routing table. What happened here? Well, what happened here was the moment when you say redistribute connected, the moment we did redistribute connected, this interface here, this serial 020, which was treated as OSPF interface, is no longer treated as OSPF interface and is suddenly treated as the connected interface for the purposes of redistribution. So what have we done there? We have created a route map that allowed only this interface to be redistributed into EIGRP, and it filtered out this interface, and it filtered out this interface, actually this interface here. So this is why this route is now not in the routing table. Now, be very, very careful about this, because this can cause you to fail the lab. This is how it's going to work. You're going to have a task that says configure EIGRP, you're going to have the task that says configure RIP, configure OSPF, configure the redistribution, and you have the full reachability, and you're all happy in your lab. Fast forward maybe hour and a half, and you are doing tasks like BGP, or maybe you're doing multicast or whatever, and there, in that section, they tell you, yeah, for this to work, add a new loopback and redistribute it into EIGRP. And you happy, you go there, create a new loopback, redistribute it into EIGRP, you create a route map to redistribute only that one loopback, and bam, this problem hits. what happened is that you no longer have full reachability in your lab, because this interface now is not reachable by R4. I cannot ping this address and I cannot ping this address. Now mind you, I can ping the loopback of R2, that's fine, but that's not full reachability, because this address and this address are now unreachable from R4. And this is the problem. It's not the problem when you see it, when they are telling you, okay, do this now. But if they told you do this an hour later, you're not even going to think that you might need to go back and re-verify your full reachability. So be on a lookout for this. Every time you are asked to redistribute connected routes into any routing protocol, this behavior may kick in, and they are maybe setting you up to actually have a problem with reachability in your network. So how do you solve it? Well, in our case, the solution is very, very simple one. All we have to do is, in this route map, we have to add match for interface serial 0 to 0, and we are good to go. So if I add that one thing here, if I do show IP route EIGRP, now I'm seeing that I'm getting all three routes that I actually expected to get. I'm getting R2's route, I'm getting R5's loopback 0, and I am getting the link between R2 and R5. The loopback 5 or R5 is not redistributed, but it's there. So if I do show IP route on R5, there it is. This is the loopback 5, but I'm not redistributing it. So be on a lookout for this one. As I said, it's relatively basic concept. It's redistributing of connected routes, and every time you think about redistribution of connected routes, how hard can it be? Well, as you can see in iOS, even the simplest thing can be actually very, very complicated. The most important thing about the redistribution is to provide loop-free environment. That means that when you are done with your redistribution, you must not have any kind of the loops. Now, there are multiple different kinds of loops, and people call them by different names. So I like to divide loops into really two categories. One is control plane loops, and the other ones are data plane loops. Now, let me explain what I mean by that. Control plane loop is when you actually have a routing information that is looping, and the data plane loop is when you actually have data packets that are looping. These two loops are different, and they both present different kinds of challenges. Now, some of these loops can be detected easily, and some of these loops can be detected less easy. Now, the best way to actually detect data plane loops is to run ping and see if everything is reachable. If something is not reachable, run traceroute. If the traceroute starts looping, well, you have a problem. If the traffic is simply being dropped somewhere, you are having a black hole, but not necessarily a loop. But your redistribution may need some examination. Now, control plane loops might be a little bit more difficult or a little bit less difficult to find, depending on your point of view. They are most easily found with a simple debug, and that is debug IP routing. Now, debug IP routing is, generally speaking, very silent. If everything is okay, again, generally speaking, it will be very, very silent. It will produce almost no output. There are some exceptions, and those exceptions have to do with the default route. If you have the existence of the default route, you might see it being refreshed in the routing table from time to time. Or if you have BGP session that is coming up, you might see some hits on the routing table that are actually going to be seen by the debug IP routing, because when the BGP session comes up, the neighbors need to verify, if external BGP session comes up, the neighbors need to verify if they are directly connected. When that happens, there is actually going to be a lookup in the routing table that debug IP routing will produce output for. But generally speaking, other than those couple of exceptions, and there could be others, but in vast majority of cases, it will be very, very silent command. So it's relatively safe to run in a stable environment. Don't do it in production. I'm talking about the CCI lab here. So it will be silent. It will be producing very little output, but it will show you when the route is added or removed from the routing table. If you see the routes being added and removed repeatedly in the routing table, you are fairly certain that you are dealing with the loop. So with the control plane loop. So my suggestion is, before you actually start working on your redistribution scenario in your lab, save the configurations, be happy as they are at that moment, run debug IP routing, and only then start redistribution. Why? Because when you are done, your debug IP routing should be silent. Now, that doesn't mean that you don't have the loops in your network, but it will, you will catch at least those most obvious ones. There are always exceptions and fringe cases, but I'm going to address at least some of them today. So this is your ultimate goal, to provide a loop-free environment, free of control plane loops and free of data plane loops. Now, going back to data plane loops, the data packets that might be looping are for known traffic and for unknown traffic. Now, what do I mean by that? The known traffic is the traffic for which you have the routes. So if the traffic for the routes that you actually have in the network is looping, you have a problem. But what about the traffic for which you don't have routes? Remember, the default route can cause problems for that traffic. So let's say that your entire network is using 192.168.0.0/16. What happens with the traffic sent to 10.0.0.0.0? What happens with that traffic? Is it going to be dropped somewhere, which is the correct behavior if you don't have the routes? Or is it going to be following the default route that might be looped itself? So keep in mind the traffic, or I should say, don't have the routes here. Keep an eye, keep a look at the route, at the traffic for the keep a look at those packets that might be following the default route, that may be following summaries for which you don't have more specifics. So I'm going to say here that unknown traffic is the traffic for following those, following the default routes, or that you don't have the routes for, you don't have the specifics. So this also must be loop free when you are done with your redistribution. Now, before you even start with the redistribution, you have to kind of recognize what kind of redistribution scenario you are dealing with. So I'm going to divide my redistribution scenarios here into two categories. I'm going to call, so let's say that we have redistribution scenarios. And I'm going to divide them into a simple redistribution scenario and complex. Now, contrary to popular belief, or contrary to what you might be considering simple redistribution scenario, what you consider complex, what I'm just about to say may actually sound very odd. Now, a simple redistribution scenario would be a redistribution scenario that goes along these lines. So you have task number 1 that says configure RIP, task number 2 that says configure EIGRP, configure OSPF, and task number 4, redistribute. Whatever the redistribution says. Now, this is a simple scenario. Why? Because you have clear-cut tasks. Do this, do this, do this, do this. Now, a more complex scenario is the one that says configure RIP, and let's say says redistribute from OSPF. What OSPF? Task number 2 says configure EIGRP, and it says redistribute to and from RIP, and it says here redistribute to and from OSPF. Task number 3 says configure OSPF, and it says here redistribute, for example, where needed, whatever that may mean. Now, this is a lot more complicated scenario. Why is it more complicated? Well, because in a simple scenario, we have clear-cut cases. If I configure RIP, I'm getting RIP points, and I don't have to worry about anything else. If I configure EIGRP correctly, I'm getting those points. If I configure OSPF, I'm getting those points. Now, if I mess up redistribution, yeah, I will lose redistribution points, but at least I'm getting those points. Now, take a look at the more complex scenario. It says configure RIP and redistribute from OSPF. Can you actually get RIP points without correctly configuring OSPF? You cannot, because you are expected to get those routes in RIP. Now, take a look at the OSPF task. It says redistribute where needed, let's say for full reachability. Can you actually get OSPF points unless your whole network functions correctly? The answer is no. You cannot get those points because OSPF task requires redistribution where needed to have full reachability. So if you don't have full reachability, no OSPF points. Take a look at EIGRP task. Redistribute to and from RIP. Can you get EIGRP points unless you get OSPF points? You cannot, because OSPF is redistributed into RIP, and RIP is then redistributed into, and you get the idea. So this is a big bowl of very, very complicated stuff. Now, when you have a complex redistribution scenario, what you need to do is you need to make it simple for yourself. So you need to simplify it yourself. You need to translate these tasks, these complex tasks here, into a set of very simple tasks. So you need to figure out that what you need to do is you need to configure RIP, and actually at this point don't do the redistribution. What you need to do is you need to configure EIGRP and don't touch any redistribution. You need to then configure OSPF and not touch any redistribution. And then you create for yourself a fourth task, which is basically going to be redistribution. So this one here, this one here, this one here, and this one here. Basically, what we have done is we have translated the complex requirements into a set of very simple steps. So these are the two possible scenarios that you can have in the lab. Now, mind you, I was using these here just as examples. It can be any wording in the text, but you are hopefully understanding what I consider to be a simple scenario and what I consider to be more complex scenario. So no matter which one you have, simple or complex, you are going to be faced with a simple question in your redistribution scenario. Is it possible for a loop to form in this network or in this scenario? So this is the question that you need to ask yourself. Please pay attention that the question is not will the loop form, but the question is it possible for a loop to form? Now, to answer this question, what you need to do is you need to simplify the network diagram that you are dealing with. So let's say that you had a network diagram that looked something like this. Now, if you have a network diagram like this, good luck. And let's say that this network really was divided into two parts, like this. And that this part here was running OSPF, and that this network here, this part of the network, was running EIGRP. And that this router here was the router that was tasked with redistribution. Now, this network diagram, as it is, can actually be simplified. And let's say that this router here is, let's say, R1. This network diagram, for the redistribution purpose, can be shown as this. This is it. You don't care about anything else. The only thing that you care about is the redistribution point. And then read the task. What does the task say? What should I do in this case? Well, there are a couple of possible scenarios here. Now, one possible scenario is that the task says redistribute from OSPF into EIGRP. So if you have this scenario here and you ask yourself a question, is it possible for a loop to form in this scenario? Is it possible that there is an OSPF route here that is going to be arriving at the redistribution point, go into EIGRP and come back here to this router and be better than the route that was actually injected by R1? The answer to this question is no. In this case, the loop cannot form. Now, if the answer to your question, can the loop form, is no, there is nothing special you need to do. You just go ahead, you implement a very, very simple redistribution, and that's it. You are done. Now, a slightly more complex scenario would be if you are asked to perform a mutual redistribution between OSPF and EIGRP. So if the task says, do this. Now, is it possible for a loop to form in this scenario? Now, the answer is still no. We cannot have the OSPF route that was best on R1, then comes into EIGRP, is injected by R1, and then it comes back and is better than R1's injected route. That's not possible. Also, not possible that we are going to take EIGRP route, injected it into OSPF, and learn it as the route better than injected by ourselves. So even in this case, we are going to have a situation that we cannot have the loop. Again, a very simple redistribution scenario. Now, even more complicated case would be if we have a situation that we have multiple routers that are performing redistribution. So let's say that we have R1 and R2 doing the redistribution here. So I'm going to have R1 and let's say R2. So I don't care how they are actually connected to the rest of the network. The only thing that I care about is that I'm asked to perform redistribution like this. So both R1 and R2 are redistributing, but only from OSPF into EIGRP. There is nothing redistributing these routes back. Now, in this scenario here, I have a lot of opportunity for very, very bad routing, for suboptimum paths and God knows what, but can the loop form? The answer is no. Very, very, very unlikely. It's not possible for a loop to form. Now, what happens in this scenario here if I'm actually asked to implement a mutual redistribution, let's say on R1, and one-way redistribution on R2? Now, in this case, it's perfectly conceivable that we are going to have the route that is OSPF route that arrives to R2, is being injected here, and arrives at this redistribution point here with, say, lower admin distance than this route. Now, this is not a route injected by R1. This is a route injected by R2 by another router. So no loop prevention mechanism in EIGRP or OSPF is going to prevent this. And I might actually inject the route back into OSPF domain that could loop. Now, mind you, internal OSPF routes and internal EIGRP routes cannot loop in this case. This is only when you have some externally injected information. So if there was some external route here or external route here. But this is that danger that I was telling you about. The question is not, will the loop form? The question is it possible for a loop to form? And there is a possibility of loop forming here if I had external routes. And if there is a possibility, you can be fairly certain that in the lab they have found a way to create the loop for you. So in this case, the answer to the question, can the loop form, is yes. The loop can form. Now, if the answer is yes, means that you have to do something about it. I'm going to get to that in a moment. Now, in this scenario, for example, when you had mutual redistribution at multiple points, the answer to the question, can the loop form, is not yes. So the answer here is not yes. The answer is, oh, yes. So in this case here, you are more than likely to have a loop. Now, mind you, again, the question here is not will the loop form, because again, if you have only internal EIGRP routes and only internal OSPF routes, it's very unlikely for this loop to form. There will be no loop, but add the externals and yeah, you will have the loop in this scenario. So when the answer to your question is yes, or in this case, oh yes, there is something that you need to do to prevent the loops from happening. Now, that something is some sort of filtering. So let's take a look at, again, the scenario where we have, let me actually reuse the previous page, so just one second here. So if we had a scenario like this, what we need to do here is we somehow need to prevent these loops from happening. So let's say that here I'm running OSPF, whatever the protocol is, and let's say that here I'm running EIGRP. And I actually have two redistribution directions. I have this redistribution direction here. So the routes are being redistributed from R1 into EIGRP and from EIGRP to OSPF by R2. And I also have this redistribution direction here, which basically moves in the other direction. So I have this flow of redistribution and I have this flow of redistribution here. Now, when I have this situation here, what I need to do I'm missing something, just one sec. So what I need to do here at this point here, at the blue redistribution here, what I need to do first is I need to deny the routes that may have been the original EIGRP routes that were redistributed into OSPF and are now trying to come back here. And I need to permit or allow original OSPF routes from coming back in. Or not coming back in from, but I need to allow them to come in to EIGRP. Now, at this red redistribution point here, I need to do the exact same thing. At this redistribution here, at this red redistribution here, what I need to do, so let me just copy this because I will be needing it a couple more times. So at this red redistribution here, I need the exact opposite logic. I need to deny the original OSPF routes and I need to allow the EIGRP routes. At this redistribution here, this blue one here, I need the exact same logic. Now, how am I going to do this? There are multiple methods. Now, usually at this point in my classes, I hear people screaming, tags, 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 use the route tags. Well, what happens if in your lab route tags are restricted? What are you going to do? What are the methods for filtering that you can use here? Well, the good news is that for this, at the redistribution point, we are going to be using route maps for filtering. Now, the good news is that in route maps, I can use access lists, I can use prefix lists, I can use route tags. In a case that BGP is involved, I can use communities. I can use even, so excluding the route maps, so at the redistribution point here, I can also use admin distance tricks to filter some routes. I can use maybe even distribute lists. I can use offset list for protocols that support it. So I can use, so this would actually require me to use ACLs or prefix lists. So I can have many different methods how I can actually make this happen. Now, what I want you to remember is not the tool. So don't remember the tool. Don't remember, oh, I'm going to use route tags for that. Because if the tool is restricted, you are going to get stuck. Remember what needs to be done. Now, obviously, and of course, if you are not restricted from doing it, of course, you are going to be using route tags for this. But it's very, very important to realize that in the CCI lab, certain tools, and that involves route tags, could be restricted from you. So let's take a look at the solution for this task here using those route tags. Now, using the access lists or using the prefix lists is going to be relatively simple solution. All you have to do is just get the list of OSPF routes, get the list of EIGRP routes, create the prefix lists or access lists, and then allow or deny based on them. But for route tags, it involves a little bit more work. But with route tags, what you are actually going to be having is much more scalable solution. Because with prefix lists or access lists, what you are going to have is that every time you add a new route to either OSPF or EIGRP, you actually need to update your access list or prefix list. With route tags, you don't really have to do that. So this is the logic that we have to implement. So we have to decide which tag we want to use for OSPF routes and which tag you want to use for EIGRP routes. Now, you can use any value you desire. You can use 1 and 2 or 15 or 19, but a good suggestion is to actually use the same value that you use for admin distance. Why? Because that way when you take a look at the route, when you look at the route tag attached on the route, you can immediately tell what was the origin of this route. If you see the route that has route tag 90, you know, oh, okay, so this was the original EIGRP route. If you see it with 110, oh, this was the original OSPF route. And you get the idea. So what we basically need to do here, so let's implement this filtering here. So what I'm going to do now, I'm going to take all of this stuff, going to perform a little magic trick. So I'm going to put it a little bit to the side. So let's implement the logic for, let's say, R1 blue. So let me just do a little divider here. So let's do R1 blue configuration. So this is R1 blue. So what I need to do here is I need to create a route map. Let's say this is going to be OSPF to EIGRP deny 10, and I'm going to say here match tag. I'm going to deny 90, and then I'm going to have, well, pretty much this. So route map OSPF to EIGRP. This is going to be permit now. 20, and I'm going to have, instead of match tag, I'm going to have set tag. $110. Now let's do R2 red. So this is the next one, R2 red. And you know, good news, very good news. Copy, paste, and we have the red logic on R2. Let's do R1 red, or actually let's do R2 blue. So R2 blue. Well, good news again, the logic is almost identical. So let's copy this, clone here. And this is going to be now EIGRP to OSPF, so this changes. So this is going to be EIGRP to OSPF, EIGRP to OSPF, and again, these two swap sides. So this is going to be 110, and this is going to be 90. And let's do, last but not the least, let's do R1 red, which is going to be, good news, this exact same configuration here. Except we need to change a couple of things here. So this is not correct. Like so. Let's move it up here, and the color changes to red. So what I've been doing here with my copy-paste on my whiteboard, you can do in the terminal. So you see, done. I have my redistribution done. What I have done here is I have written the logic only once, and then I have copy-pasted it and just modified the values a little bit. So this is the solution that you can use when you have mutual redistribution at two points between two protocols. But what happens if you have 3 or more protocols? The question I have is, does it matter what is the order of operation for redistribution between different routing protocols? If you solve it correctly, the answer is no. But if your solution is incorrect, you have to realize that sometimes you are going to have different behavior depending which routes are learned first. So if you have that situation, it means that you don't have a deterministic behavior in your network, which is generally speaking not a good idea. So what you need to do is make sure that no matter in which order your routes are received, your network always works. So for those of you who might be attending one of our workshop classes, there is a lab in that workshop class that actually addresses this particular behavior. It has this order of operation landmine hidden in there that we don't warn you in the text of the lab, but you have to figure out that is happening. But my answer stays, if you solve your lab, your redistribution correctly, it shouldn't matter. But if your solution is incorrect, or if you don't understand how these processes of redistribution work, you might have that problem, that the order of operations actually matters. But your solution should not take that into account, because when you are being graded, you don't know what is going to be the order. They could be bouncing the interfaces, they could be changing the order in which routes are learned, so you should always have a deterministic behavior. When we have more than 2 protocols involved in our redistribution scenario, things are a little bit more complicated. So let's take a look at that example. So I'm going to have now 3 protocols, and again, I'm going to simplify my scenario here. I'm just going to divide my network into 3 parts. I'm going to have 3 routers doing the redistribution. So let's say that this here is my R1, let's say that this is R2, and let's say that this here is R3. And let's say that I have OSPF, I have EIGRP, and let's say that I have RIP on this side here. So this is the basic network setup, and I'm asked to redistribute like this. So mutual redistribution at 3 points with 3 protocols. So this is the setup, this is the scenario that I have. Now, let's take a look at what happens here. I can implement the exact same logic that I implemented before, and this was the logic that worked like a charm for me before. So I had deny source and deny destination and allow the source protocol. So let's just implement the exact same thing. So here on R1, let's say that my first line is going to be deny OSPF, deny EIGRP, and that I say tag everything as OSPF. That here I have the logic that says deny RIP and tag everything else as EIGRP, and that I have the logic here that says deny OSPF and tag everything else as RIP. And I'm going to repeat the same thing for blue logic. So here I'm going to have deny EIGRP and tag everything else as RIP. So I'm going to have the same thing here, deny RIP and tag everything else as OSPF. And logic that I'm going to implement on this side, so I just need a little bit more space here. So the logic that I'm going to implement here is going to be deny OSPF and tag everything as EIGRP. So this is the logic that I might implement. Now, let's see how this works. I'm just going to take a sample route, and this sample route is going to be an original OSPF route. So let's follow the path of this OSPF route when it arrives at this redistribution point here. Is it EIGRP route? No. That means it will be tagged as OSPF. So this route now arrives at this redistribution point, and it has the tag of 110. Is this a RIP route? No. That means tag it as EIGRP. That means that this route now arrives at this redistribution here with the tag of, let's say, 90, which means that this route is now going to make its way back into OSPF domain, and I have actually created a loop. So the logic that worked like a charm for me just before has now failed miserably. Now, the reason why this logic failed is because here we have lost the information that this was an original OSPF route. We have retagged this route as, we have lost information that this was an original OSPF route. We have retagged this route as 90, which means that this route arrived to redistribution into OSPF with R3 thinking that it's dealing with EIGRP and not the original OSPF route. So what we need to do is somehow preserve this tag here. So to do that, we need to have one more entry in our logic here. Now that one additional entry in the logic is going to be sitting here in the middle. And this is going to be the match RIP in this case. In this case here, it is going to be match OSPF. In this case, it's going to be match EIGRP. And let me just add match. And in this case here, it will be OSPF. And in this case here, it will be EIGRP. And in this case here, it will be match RIP. So let's take a look at how this logic will work in a previous example. So we have this original OSPF route that arrives here for redistribution. Is it EIGRP route? No. Is it RIP route? No. Is it OSPF route? Yes, which means it will get tag 110, and now we are arriving here. Is this RIP route? Answer is no. Is this OSPF route? The answer is yes, which means it keeps its tag and arrives at this redistribution here. Is it OSPF? Yes, and it's being denied here. So we have prevented the loop. So we can say that here the loop was actually stopped. Now, the generic logic for this here is very, very simple. Every time when we are redistributing, we have a source protocol that is being redistributed into the destination protocol. Now, behind the source protocol, we might have some other protocol, and we may have multiple others. So the logic that we have to implement at this redistribution point here is very simple. Deny destination, match other, and if you have multiple others, you simply add those multiple match statements. And finally, we have tag source. So this is the generic logic that you can implement for tagging. This will work with two protocols. Well, not with two because you don't have the other, but this will work with 3 protocols. It will work with 4 protocols, 5, 19, 57 protocols. But there is a problem with this logic. Now, the problem with this logic is, and I'm going to illustrate it by just copying this page for a second. The problem with this logic is when we have this tag here. Now, this tag now exists in EIGRP route. So this tag exists as EIGRP route. When we inject this route here at this point, we need to generate, from EIGRP route, we need to generate a new RIP route. Will the tag actually be copied as this new generation happens? Now, as it turns out, when you have RIP to OSPF, the answer is yes. When you have RIP to EIGRP, the answer is yes. When you have EIGRP to RIP, the answer is no. When you have OSPF to RIP, the answer is no. When you have OSPF to EIGRP, the answer is yes. And when you have EIGRP to OSPF, the answer is yes. Please repeat. I'm pretty sure that you are guessing that it has something to do with RIP, but you are not entirely sure in which direction. This is why I would like you not to remember this. Do not remember. Why don't remember? Because A, Marco thinks this is true, and B, probably somewhat iOS specific. So you might be at the mercy of the iOS version. That's the last thing that you want to have in the CCI lab. Now, the reason why I tell you don't remember this is that there is actually a solution for this, even without actually caring about whether the tag gets copied or not. So this is the logic that we implemented. So let me work on this page. Instead of doing just a simple match, what we are going to do here is we are going to have this second entry that is going to be match and tag. This is how one route map entry might look. So I'm not going to do all of them because that will require me a lot of writing right now. So I'm just going to do one of them. So let's do this one here. So I'm just going to write out the route map for this. So what I'm going to have here is route map, let's say OSPF to EIGRP, deny 10. Then I'm going to have match tag 90. Then I'm going to have route map OSPF to EIGRP, permit 20. I'm going to have match tag 120, and then set tag 120. And then I'm going to have route map OSPF to EIGRP, permit 30, and I'm going to have simple set tag 110. Now, this part here, when you first see it, looks a little bit confusing. Now, the important thing here to note is that this match tag takes effect against the incoming OSPF route. This set tag takes effect on outgoing EIGRP route. So basically, match tag matches the source route, so whatever we are receiving from the source, and set tag is the action that we are going to take when we actually generate the route for the destination routing protocol. So technically speaking, the tag 120 here and the tag 120 here is not the same tag, but it has the same value. Do I actually care that the same bits, the same electrons were not actually used to generate this new route? I couldn't care less, as long as this value here matches this value here. And with this approach, I'm avoiding having to actually remember when the tag will be copied when the route gets generated. I don't have to worry about that one little bit. Now, another important thing to remember, that this system of tags is actually a system. that means that there is not a single filter, there is not a single route map entry here that prevents the loop. It's the whole system that prevents the loops. So if you listened to my advice and before going into the redistribution, you have enabled debug IP routing, when you start doing this stuff, when you start redistributing with a logic like this, your debug IP routing is going to go absolutely crazy. Now, that's okay, because you have to trust that it will be the system that prevents the loops. Now, just like any system, this is effective up to a point. I would say that about 99.99, maybe even one more 9 here, % of the cases, this will prevent the loops. Now, there are some loops that cannot actually be stopped by this system. So I'm going to give you one example now. So this is where tags don't work. And as I'm saying, this is just one example of it. This is the example that I'm going to be using to show you how you may actually have trouble with tags stopping the routes. So let's say that you have a scenario in which R1 and R2 are running OSPF0, R2 and R3 are running OSPF23 and SSA, and you have R3, R4, and R5 here running RIP, and then we have R6, R5, and R2 running EIGRP. And the task is very simple. Make sure that everything in this network is reachable, mutually redistribute between R2, or on R2 between OSPF and EIGRP, on R3 between OSPF and RIP, and on R5 between EIGRP and RIP. So this is the task. And by the way, on R6, you need to redistribute this 6.6.6.6 into EIGRP. Now, you catch that there is a possibility of a loop forming here, because this is a mutual redistribution between three protocols on 3 devices. So the answer is it possible for a loop to form here? Is yes, it is conceivable that a loop will form. So you go in and you implement your tags-based solution. Now, if you don't implement tags-based solution, you're going to have a full reachability in your network, except for 6.6.6.6. With 6666, you are actually going to have a problem reaching it from R1 and R2. Now, when you implement the tags, that problem most likely goes away, and you have full reachability in network. All good and all fine. So tags are now in place. So you have configured the tags, you have configured your redistribution, so that is all in place now. And now the next task comes in. The task says on R2, inject the default route into your NSSA area. You do that and there is no problem. Now R3 learns this default route, and this here is the next hop for this default route. R3 is configured to redistribute from OSPF into RIP. So this default route now gets advertised to R4, and this here is the next hop for that route. R4 here advertises this route to R5, and this is the next hop for that default route. That's all good. Now, this route, being original OSPF route, is now going to be redistributed into EIGRP and advertised to R6. So R6 is now going to have the default route with R5 as next hop. This route is also going to be advertised to R2. So R2 now has the default route with this as next hop. But mind you, this is an original OSPF route, which means that this default route will not be advertised to R1. Loop prevented. Well done. Now we go to R6 and let's do the trace route to 10, 10, 10, 10. Now you can see here that the network in use in our system here, in our network, the subnet in use in our system is 192.168.00/16 and subnets of it. So 10, 10, 10, 10 is the network that we don't have the path for. So what do we do? Well, actually, this goes here. What happens is this packet for 10, 10, 10, 10 now goes to R5. It follows the default route. R5 has the next hop of this default route, which is R4. The traffic is sent here. R4 sends the traffic here. R3 sends the traffic here. And R2, in its routing table, has the default route with this as next hop. R5 then sends it here. What we have is actually a loop. Unknown traffic in our network is actually now looping as the result of a simple injection of the default route. Now mind you, the tags have prevented this route from going back into OSPF, but they have not prevented R2 from learning the route it generated itself. Because when you generate the route into the OSPF NSSA area, there will be no discard route installed on R2. So when R4 advertises this route to R2, you will have a loop for the traffic that you don't have more specific routes for. How do you stop this from happening? Well, as it turns out, multiple ways. You can filter this route here, you can filter this route here, you can filter this route here, here, or here. The only router where you need to have this route is R3, because this is the only thing that the task actually requested you to do. They said generate the default route into the NSSA area, which means that R3, which is the only router in the NSSA area other than R2 who generates the route, is the one that needs to have this route. All other routers don't need to have it. But there is one router that must not have this route, and this is R2. So it is okay to have this route on any other routers except for R2. And you must have it on R3, because that was the only requirement of the task. So here is just one example when tags don't actually solve the problem of the loops. As I said, just one simple example.